Let me put you in a room. It's colder in there than the empty space between the stars, and it's dead quiet. And on a small table, there's a ring of metal, just a plain loop like a wedding band, sitting in a bath of something clear and cold. Somebody gives the electrons inside that ring a single push, sets them circling, a current going round and round the loop, and then they do the strangest thing. They walk away. They come back the next morning, still going round. The next week, still going. Next spring, next year, they check again, and that current is still circling the ring, exactly as fast, having lost not a whisper of its energy, with absolutely nothing pushing it. And right beside it, in a little cup, there's a liquid so cold it shouldn't do anything at all, and it's climbing, creeping up the inside of the glass, over the lip, down the outside, siphoning itself onto the table drop by drop, as if friction had simply been switched off. Two substances, one impossible-looking gift.
And I'll promise you right at the top, neither is a trick, neither is a metaphor. That current really does go round for longer than you'll be alive. That liquid really does climb out of its own cup. Two of the most literal, hold-it-in-your-hand strange things in physics. And in the next 40 minutes, I think you'll understand why. Because they turn out to be the same secret, wearing two costumes.
Okay, but you know my first reaction. 2 years of physics now, and I feel like I've met both of these before, in pieces.
Go on, say the sentence. I can see it coming. Wait, isn't this just resistance going to zero?
Isn't this just resistance going to zero? I know what electrical resistance is, and I know matter changes phase. Water freezes to ice at a sharp temperature. So the ring, a wire whose resistance dropped to zero. The climbing liquid, some phase transition. Two things I already learned, stapled together. Tell me why I'm wrong to be so calm about it.
You're not wrong. You're exactly right. And that's the wonderful part. You've just named the two ideas this whole episode is built out of, and you're about to walk from your homework straight to the edge of what anyone knows. First, resistance. In your electricity and magnetism course, why does a wire have resistance at all?
Electrons drift through the metal carrying current, and they keep banging into the atoms. The lattice, a grid of positive ions, jiggling because it's warm. The electrons scatter off all that jiggling and off any defects in the grid. Every collision, an electron loses a bit of energy to the lattice, and that shows up as heat.
Which is why your laptop charger is warm. That warmth is the tax every electron pays, collision after collision, heating the metal. Resistance is just friction for electrons. Now hold that and pick up the second idea. Phase transitions. Water to ice. What's special about the temperature where it happens?
It's sharp. You cool water. Nothing, nothing, nothing. And then, right at the freezing point, it doesn't gradually stiffen, it flips. The molecules lock into a crystal all at once, a completely different state with completely different rules. A phase transition isn't gradual, it's a switch.
A switch. Now here's the whole question of the episode. You've got resistance, friction for electrons, always warming the wire. And you've got phase transitions, a sudden flip into a new state at a sharp temperature. So, what if a metal, cooled past some critical temperature, didn't just get less resistive, but flipped, sharply, like water to ice, into a state where the resistance wasn't small, wasn't tiny, but exactly, perfectly zero?
Exactly zero. Not too small to measure, actually zero.
Actually zero. And that's the difference that turns a homework problem into a 100-year mystery. If it's genuinely zero, the electrons pay no tax at all. You set them going and nothing slows them down, ever. That's your current that never stops. Though I should be honest about that word, never.
Please, I was about to push on it. Forever is a big claim.
It is. Persistent currents in these rings have been watched for years with no measurable decay. And if you work out how slowly one could possibly leak away, the time comes out longer than the age of the universe. So it's not literally infinite, it's, for all practical purposes, forever. That's the forever I mean, and I'd rather you have the honest one.
I'll take the honest one. So who found this? Who first cooled a wire far enough to see the switch flip, the day the resistance vanished?
A Dutchman named Heike Kamerlingh Onnes in Leiden at the start of the last century, and he'd already won a race no one else could. To get anything that cold, you need a coldant, and the coldest liquid there is liquid helium. Helium does not want to be a liquid. You have to drag it down to about 4 degrees above absolute zero before it gives in. In 1908, Onnes became the first person ever to hold liquid helium. For a while, his lab was the coldest place in the known universe.
So he builds the coldest fridge in existence, then starts throwing things in it to see what happens.
Essentially. And the burning question was, what does resistance do as you approach absolute zero? Real theories said it might get worse. The electrons might freeze in place and the metal stop conducting. So in 1911, Onnes cools a thread of very pure, frozen mercury in his liquid helium, watching the resistance the whole way down. And at about 4 degrees above absolute zero, it doesn't drift or bottom out at some small value. It drops off a cliff, vanishes abruptly to nothing he could measure. He wrote that mercury had passed into a new state, which, he said, might be called the superconductive state.
A new state. That's phase transition language. Water to ice, like I said. He knew right away it was a new phase, not just really good wire.
He knew it was sudden and total, which smelled like a phase transition. But the full proof that it's a genuinely new state of matter took another 20-odd years. In fact, Onnes won the Nobel Prize in 1913, and if you read the citation, it's for his low-temperature work, for liquefying helium. It doesn't single out superconductivity at all. The discovery was so new, it wasn't even the headline on his own prize, and it would sit there, an astonishing fact with no explanation, for the better part of 50 years.
A Nobel where your most famous result is basically a footnote, because nobody understood it yet. So what was the missing proof? What told everyone this was a new phase, not just perfect wire? The clue that it's a new state of matter.
This is my favorite turn in the story, and it's easy to get wrong. Suppose I told you a superconductor is just a perfect conductor, a wire with exactly zero resistance, full stop. Sounds complete, right?
Sounds like the whole thing. Zero resistance, current forever, done.
So let's test it. Picture a lump of ordinary metal in a magnetic field lines threading through it. Now cool it until it becomes a perfect conductor. What happens to the field inside?
A perfect conductor. If you tried to change the field, the electrons would swirl to oppose the change. Induction, Lenz's law. So it should lock in whatever field was already there. The field threading through when it cooled would get trapped inside, frozen in place.
Exactly. A merely perfect conductor traps the field it was born with. That's what zero resistance predicts. Now, in 1933, 2 physicists in Germany, Walter Meissner and Robert Oxenfeld, did the experiment on tin and on lead. And they found the opposite. When the metal crosses into the superconducting state, it doesn't trap the field, it throws it out. Actively shoves the field out of its own interior until there's essentially zero field inside, even a field that was already sitting there.
That's genuinely different. Trapping is passive. I won't let you change what's here. Throwing it out is active. It's doing work to clear itself.
You've put your finger on the whole thing. And that difference means a superconductor is not just a perfect conductor, it's more. That active expulsion, the Meissner effect, is the telltale sign that superconductivity is a true thermodynamic phase transition, a genuinely new state of matter with its own rules that the metal flips into at the critical temperature. Your water-to-ice switch, but for the electrons and the magnetic field together. Not a very good wire, a new phase.
And this is what makes a magnet float. Those pictures where a little magnet hovers over a cold black tile.
Exactly. The superconductor won't let the field in, so it pushes back on the magnet, trying to poke field into it, hard enough to hold the magnet in mid-air. The floating magnet isn't a trick bolted on the side, it's the Meissner effect made visible. So, we have the what? A sharp flip, resistance exactly zero, field expelled. What we don't have is the why. Why would cooling a metal do all this? That took the best physicists in the world nearly 50 years, and it's the most beautiful idea I get to tell you today.
That's the one I want, because right now I have zero intuition for it. Electrons repel each other. How does making them cold do anything but make them repel harder? Why electrons that hate each other decide to dance?
Right, and let's honor that, because it's the whole difficulty. Every electron is negative, two near each other push apart hard. Coulomb repulsion, straight from your first week of E and M. So any story where electrons cooperate must explain how the most antisocial particles in the wire team up. 4 steps, slowly. Stop me at each one.
Deal. Step 1.
Step 1 just sharpens the puzzle. Resistance is scattering, electrons colliding with the jiggling lattice and losing energy. So how could scattering ever stop completely? As long as there's a warm lattice and the electrons rattle around in it independently, they'll scatter. Cooling helps a little, but never quite gets you to exactly zero. Independent electrons in a warm grid always scatter something. So whatever's happening down there, the electrons must have stopped being independent. That's the only way out.
So the trick isn't make the lattice perfectly still, it's make the electrons stop acting one at a time. Got it? Step 2.
Step 2 is the counterintuitive heart. A picture, and I'll flag where it lies. An electron flies through the metal, negative charge, and as it passes, it tugs the positive ions of the lattice a little toward its path. Those ions are thousands of times heavier, so they respond slowly. By the time they've drifted toward where the electron was, it's long gone. But for a moment, it's left a knot of extra positive charge. Ions bunch together in its wake. And a second electron, coming along, sees that knot of positive charge and is drawn toward it.
Oh, so the second electron isn't attracted to the first electron. It's attracted to the dent the first one left in the lattice, the positive wake.
Exactly right. And that's the crux. The two electrons never have to like each other. The lattice plays matchmaker. Electron 1 dents the grid. Electron 2 rolls into the dent. The net result is a weak, indirect attraction between them, carried by the vibrating lattice. That vibration, as a quantum thing, has a name, a phonon. But what you need is the dent. 2 electrons bound loosely through the lattice into what we call a Cooper pair, after Leon Cooper, who worked it out.
Can I have the analogy version? I want to picture it, but you said you'd tell me where it breaks.
I insist on both. The cartoon. 2 heavy bowling balls on a soft mattress. Each makes a dent, and each rolls toward the other's dent. So they act attracted, though the balls never touch. It's all through the sagging mattress. Good picture of attraction through a deformable medium. Now, 3 ways it lies. First, the real attraction is fantastically weak, nothing like 2 balls thudding into one pit. It's the faintest tug, which is exactly why you must go so cold. Any thermal jostling drowns it out. Second, it works only because the ions are slow. The whole effect lives in that lag, the dent lingering after the electron has left. If the lattice snapped back instantly, no wake, no attraction. It's a delayed attraction, not a static one. And third, the big one. Because of that lag, the two electrons in a Cooper pair are far apart. Hundreds, even thousands of lattice spacings, with a crowd of other electrons in between. So don't picture a tidy two-electron molecule, two balls in a pit. Picture two dancers on a huge crowded floor, partnered, moving in response to each other, while separated by half the room.
That's a much stranger picture. They're partners, but nowhere near each other, and the partnership is really just a correlation, carried through the whole crowd.
A correlation carried through the whole crowd. You just said in plain words something it took people years to say in equations. So, what difference does pairing make? Here's the magic. A single electron is a fermion, and fermions are the antisocial particles of the universe. No two can ever be in the same quantum state. That's the Pauli exclusion principle, the thing that stacks electrons into shells and gives you the whole periodic table. Fermions refuse to pile up, but bind two fermions into a pair, and the pair, as a unit, behaves like a boson. And bosons are the opposite, gregarious. Not only can many bosons share one quantum state, they want to. They pile in.
Wait, that flip is doing a lot of work, and I want to be sure I'm not being sold something. Two antisocial particles glued together become one social particle. Just because two halves make a whole.
Push on it. It's not hand-waving, but the honest version has a fence. Behaves like a boson is a statement about counting, about statistics, the rules for swapping identical things. Pair two fermions, and the pair follows boson counting, which permits, even encourages, many in the same state. What it is not is a claim that a Cooper pair is a hard little particle you could pluck out and hold up. You can't. The pair is spread across half the room, overlapping heavily with millions of other pairs. It only exists as a pair because of all the others around it. So it's like a boson is about the social rules it obeys, not about it being a tidy object. So yes, the pairs do what bosons do,
Which is pile into the same state, so all the Cooper pairs in the wire
drop into one and the same quantum state. Every pair, described by a single shared wave function spanning the entire wire, a centimeter, a meter, kilometers of it. And this should stop you cold. Quantum mechanics is supposed to be the physics of the very small. One atom, one electron, the double slit. Here, the whole population of pairs locks into a single quantum state you could hold in your hand. A macroscopic quantum phenomenon. Quantum mechanics at human size. That ring on the table, with its endless current. That is one quantum state, big enough to see.
That genuinely gave me a chill. But you still owe me the punchline. Why does that kill the resistance? Why does being one big shared state mean the electrons stop scattering?
Step 4, and it almost falls out on its own. Resistance is scattering, one electron at a time, losing a dribble of energy. But now the electrons aren't traveling one at a time. They're locked into a single collective state. So to scatter one electron, the lattice can't just nudge that one anymore. It would have to rip a whole pair out of the shared condensate, break it from the lockstep of all the others. And that costs a specific minimum chunk of energy, the energy gap, a gap between the locked-together state and the next thing up. So, at low enough temperature, the lattice's little thermal kicks are all smaller than that gap. Not one can pay the toll, so not one scatters anything. The electrons sail through, collectively, untouched, and the resistance is not small. It's zero, truly zero, because there is no available way to lose energy at all.
Oh, that's the whole thing. It's not that the electrons dodge the lattice, it's that there's no move the lattice can make big enough to disturb them, as long as you stay below the gap. They're protected by being together.
Protected by being together. That's the sentence. and it pays off the Meissner effect for free. Why does it expel magnetic field? To let a field thread through, the condensate would have to change its locked-in state. And it resists that for the very same reason it resists scattering. So it sets up currents on its own surface that cancel the field inside and push it out. Zero resistance and field expulsion aren't two facts. They're one fact, the rigidity of a single coherent quantum state, seen from two sides.
That is so much better than a wire with no resistance. So who finally wrote this down?
1957. Three physicists in the United States, John Bardeen, Leon Cooper, and Robert Schrieffer, published the theory in Physical Review. We call it BCS theory, from their initials, the first time anyone explained superconductivity from the ground up, about 46 years after Onnes watched the mercury drop to zero. They win the Nobel Prize for it in 1972. And the detail I can't resist, that was Bardeen's second Nobel Prize in physics. His first, years earlier, was for co-inventing the transistor. He's the only person ever to win the physics Nobel twice. The same man explained the transistor your digital world runs on, and the reason a magnet floats.
The same person did the transistor and this. That's absurd. Okay, you promised me the climbing liquid was the same secret. I haven't forgotten. Where does the helium come in? The same trick, with no charge at all.
Here's where it gets even prettier, because it shows the idea is bigger than electrons. Go back to the liquid helium Onnes made. Cool it further, past about 2 degrees above absolute zero, a point we call the lambda point, and the helium itself does something outrageous. It becomes a superfluid. Its viscosity, its internal friction, the thing that makes honey pour slowly, drops to effectively zero. It flows through cracks too fine for any ordinary liquid, and it does the thing from the top of our episode, creeps up the walls in a thin, invisible film, over the rim, and siphons itself onto the floor. It empties its own cup, because there's no friction to hold the film back.
So that's the climbing liquid, real, superfluid helium. And it's the same physics as the electrons in the ring. But there's no current here, no wire, no charge, just atoms.
Just atoms. That's the point. Strip away the electricity, and the deep idea survives. The shared skeleton, a crowd of identical quantum particles, cold enough, all dropping into one shared quantum state, a condensate, that flows without friction because there's no cheap way to disturb it. For the electrons, the particles were charged Cooper pairs, so that frictionless flow shows up as current with zero resistance, plus the Meissner effect. For helium, the particles are neutral atoms, no electricity, so the flow just shows up as literal flow, liquid moving with zero viscosity. Same skeleton, different costume.
I have to do the analogy police thing here, because you trained me to. Superfluid helium is just a superconductor for neutral atoms. Where does that break?
Hold me to it. There's a real seam. The shared part is genuine, a condensate of identical particles flowing without friction, the same in both. But electrons are charged and helium atoms are neutral, so everything electromagnetic belongs only to the superconductor. Currents, magnetic fields, the Meissner effect, all need charge, so helium just doesn't have them. They share the condensate, they do not share the electromagnetism. Take the frictionless flow, leave the magnets behind.
Clean. And who found the helium version?
Announced in 1938, Piotr Kapitsa in Moscow, and independently John Allen and Don Meissner in Cambridge, back to back. And there's a wrinkle that ties it into a bow. There are two kinds of helium. The common one, helium-4, has atoms that already behave like bosons, so they condense directly, no pairing needed. But there's a rare kind, helium-3, whose atoms are fermions, antisocial like electrons. And to become a superfluid, the helium-3 atoms have to first pair up. Cooper pair, exactly like electrons in a superconductor, and only then condense, down to around 0.002 of a single degree above absolute zero.
Oh, that's the bridge. Helium-3 literally does the Cooper pairing trick before it can flow. So superconductivity and superfluidity aren't cousins. They're the same phenomenon.
The same phenomenon, wearing whatever costume the particles handed. Charged fermions that pair, a superconductor. Neutral bosons that condense directly, superfluid helium-4. Neutral fermions that pair first, superfluid helium-3. One idea, 3 outfits, and a row of Nobel Prizes. Landau for the theory of the flowing helium, Kapitsa for the experiments, later Osheroff, Richardson and Lee for helium-3, with Anthony Leggett for its theory. Everyone downstream of the same picture. Pair up, condense, flow without friction.
So, by the 1970s, this is a solved, beautiful, closed story. That feels suspiciously clean, and you've got a look on your face. The earthquake of 1986.
I've got a look on my face because in 1986, the whole thing cracked open again. Before that year, BCS works. It explains the superconductors people knew. But BCS also seemed to whisper a limit. Because the pairing glue is those slow lattice vibrations, there's only so strong it can get. So the critical temperature can only go so high. For decades, the very best superconductors topped out around 20-odd degrees above absolute zero. You always needed liquid helium, expensive and fussy. A ceiling built into the physics.
And let me guess, somebody smashed through the ceiling.
2 people nobody expected, on a material nobody expected. Georg Bednords and Alex Müller at IBM's research lab near Zurich, and they weren't testing a shiny metal, but a ceramic, a copper-oxide ceramic, a compound of lanthanum, barium, copper and oxygen. A ceramic is normally the kind of thing you'd expect to be an insulator, closer to a coffee mug than a copper wire, and this thing went superconducting at around 30 degrees above absolute zero, far above the ceiling everyone thought BCS imposed. It was so surprising they were nervous about it going out.
A coffee mug material superconducting higher than the metals do. That's backwards. What happened next?
One of the great feeding frenzies in science. The moment it got out, labs everywhere started cooking variations of this copper-oxide recipe, racing to push the temperature up. Within months, a group in the United States, Mo-Kuen Wu, Paul Chu, and their collaborators, found one that changed everything. A compound of yttrium, barium, copper and oxygen, the one everybody just calls YbCO. And it superconducts at 93 Kelvin.
You've switched units, degrees above absolute zero all night, and now Kelvin. Same scale, right?
Exactly the same. Kelvin just counts up from absolute zero. I'm saying it the short way because this number deserves its proper name. And here's why 93 set the world on fire. There's a magic line at 77 Kelvin, the temperature of liquid nitrogen. And liquid nitrogen is cheap. You buy it by the jug, pour it in the open air, and it's roughly 500 times cheaper than liquid helium. For 75 years, superconductivity had meant only inside an expensive helium bath. YbCO at 93 Kelvin was the first superconductor above the boiling point of liquid nitrogen. Suddenly, you could make something superconduct by pouring cheap nitrogen over it. Overnight, from a helium bath curiosity to something you could imagine engineering with.
That's the earthquake. And I want to flag the phrase because I keep hearing it. High-temperature superconductor. 93 Kelvin is not high temperature. That's brutally cold. Minus 180 Celsius, roughly.
Roughly minus 180 degrees Celsius, yes. You'd freeze solid instantly. So you're right to flag it. It's the most misleading phrase in the field. High temperature means high compared to the old helium temperatures. to 4 degrees above absolute zero. It does not mean warm. Every one of these is still punishingly cold. Translate high-temperature superconductor as works at the temperature of cheap coldant instead of expensive coldant. And Bednorz and Müller got the Nobel Prize the very next year, 1987, the fastest anyone has ever gone from discovery to that prize.
So this is triumphant. New materials, cheap coolant, Nobel in a year. Is there a catch? There's always a catch with you.
An enormous catch, the honest heart of the back half. But before the mystery, superconductivity isn't a promise, it's a workhorse, around you right now more than you'd think. Let me show you what all of this is quietly doing. Start with the one that may have looked inside your own body. The MRI scanner in every big hospital. It sees soft tissue, your brain, a torn ligament, by wrapping you in an extraordinarily strong, steady magnetic field. And the only practical way to make one that strong is a superconducting magnet. Miles of niobium titanium wire wound into coils, kept in liquid helium at about 4 degrees above absolute zero, with a current circling those coils that never stops. That endless current from our opening, it's humming inside MRI machines in every city on Earth. By a wide margin, the biggest everyday use of superconductivity, hundreds of tons of that wire a year just for scanners.
So the ring with the current that never stops isn't a lab curiosity, it's a hospital, keeping a magnet lit. That reframes the whole opening.
Exactly the reframe I wanted. Second, for the physicists, the Large Hadron Collider at CERN near Geneva, the biggest machine humans have built, a ring 27 kilometers around, underground, steering protons at nearly the speed of light. What bends those beams? Thousands of superconducting magnets, the same niobium-titanium family, at fields of more than 8 Tesla. And here's the detail that makes me grin. To keep those magnets cold enough, they use superfluid helium, below about 2 degrees above absolute zero. So the greatest experiment in particle physics runs on both of tonight's marvels at once. Superfluid helium keeping the superconducting magnets in the state where their current flows without resistance. Both costumes of the same secret, one machine.
Both in one ring. What's the third?
The most fun, trains that float. Japan built a maglev train, magnetic levitation, that rides on superconducting magnets instead of wheels, hovering with no contact, no rolling friction. On a test line, with passengers aboard, one set the world speed record for a train. A bit over 600 kilometers an hour, around 375 miles an hour back in 2015. A train carrying people at the speed of a small aircraft, held up by the same field-expelling, current-carrying physics we've talked about all night.
The floating train is the one that makes me want to go build something. All right, I've been patient. You said there's an enormous catch behind the 1986 earthquake. Take me to the honest edge, the honest horizon.
Then here it is, and I'll sort the pile into 3 heaps: the solid, the genuinely unknown, and the outright false. This corner of physics has all 3, tangled together, and telling them apart is the whole skill.
All 3 clearly labelled. Start with the solid.
Solid, bedrock. Superconductivity is real, about a century old. The Meissner effect is real. BCS correctly explains the conventional superconductors, the metals, the niobium titanium in your MRI. Cooper pairs are real. Superfluid helium is real. The copper-oxide ceramics from 1986 are real, Nobel-honored, running in labs worldwide. The scanner, the collider, the floating train, all working. None of that is in doubt. Now the genuinely unknown, and it's the reason I'd point a student your age right here. We do not know how the high-temperature copper-oxide superconductors actually work.
Wait, hold on. We've had them for 40 years. Undergrads float magnets with these things using jugs of cheap nitrogen, and we don't know how they work?
We do not. A sharp, specific ignorance, not a vague fog. For the conventional superconductors, BCS nailed it. The glue is lattice vibrations, the dent in the mattress we built. For the copper-oxide ones, that same glue does not add up. The numbers don't work. Something else is pairing those electrons, and after 40 years of the smartest people alive attacking it, nobody has a complete theory of what. The pairing has a different character than the BCS kind. The ordinary non-superconducting state is itself strange, unlike any normal metal. And just above the superconducting region sits a weird regime we call the pseudogap, where the material acts half-prepared to superconduct without quite committing. Whether that's pairs forming early or some rival order competing has been argued for decades.
So it's not "we're pretty sure" and cleaning up details, it's actually open.
Actually open. One of the great unsolved problems of my field, condensed matter physics. There's real recent progress. In the last couple of years, a group measured the shot noise, the tiny fluctuations in the current, in one of these materials and found evidence tying the pseudo-gap to electrons pairing up, suggesting what limits the temperature isn't forming the pairs, but getting them all to lock into one coherent state. A real clue, but a clue is not a theory, and I won't tell you it's solved because it isn't. If you want a problem both 100 years deep and still wide open, where a person your age could be the one to crack it, this is one of the best in physics.
That's the honest "we don't know." Now the thing everyone's heard about lately, room temperature superconductors, working at ordinary temperature with no coldant at all. Every so often, a headline says somebody found one. Where does that stand?
I'll be blunt. As of right now, there is no verified superconductor that works at room temperature and ordinary pressure. None. And the two most famous recent claims both collapsed. And it matters how, because it's science working the way it should.
Lay them out. Straight.
The first, Ranga Dias, at the University of Rochester, published claims in Nature of superconductivity essentially at room temperature. One paper in 2020 on a hydrogen-carbon-sulfur compound, then a bigger claim near room temperature and far gentler pressure on a lutetium-hydrogen material. Both were retracted, the first over serious problems with how the magnetic data had been processed. The second in 2023 at the request of Dias's own co-authors after independent groups failed to reproduce it and questions were raised about the data. And it didn't stop at two. By the middle of 2024, Dias had 5 retractions, including one where investigators concluded there was apparent data fabrication, and his university's investigation found research misconduct.
So this isn't a promising result that didn't pan out. Retracted, with a misconduct finding, and in at least one case, fabricated data.
That's the accurate way to say it, and I won't soften it. Retracted, misconduct found. In one case, data apparently fabricated. Those claims are not standing results, they've been withdrawn from the record. Now the second, which went viral, a material called LK99.
Oh, I saw that one. Videos everywhere. A chip half lifting off a magnet. For about a week, everyone was convinced.
For about a week, the whole internet was going to have room temperature superconductors by Christmas. In the summer of 2023, a team in Korea posted papers claiming a copper-doped lead apatite material, LK99, was superconducting at room temperature and ordinary pressure, both at once. Exactly the dream. Then the world's labs did their job. Within weeks, group after group tried to reproduce it, and it fell apart. The apparent drop in resistance and that partial levitation weren't superconductivity. They came from impurities, a bit of copper sulfide that changes structure at a certain temperature, plus some magnetic bits, faintly mimicking a superconductor. Purer samples behaved like an insulator. The verdict is settled. LK99 is not a superconductor.
So both famous "we did it" stories are gone. One retracted with misconduct, one debunked as impurities. Is there anything real near room temperature, or is the whole idea just hype and fraud?
No, and this is the part I most want you to hold on to, because it's the easiest to lose in the noise. There is a real, careful, mostly accepted frontier near room temperature, and the crucial move is to keep it separate from those collapsed claims. It's a totally different kind of science. It's the hydrides, hydrogen-rich materials squeezed under monstrous pressure. In 2015, a group in Germany found that hydrogen sulfide, crushed hard enough, superconducts at about 203 Kelvin, roughly minus 70 degrees Celsius. A few years later, a lanthanum hydrogen compound reached around 250 Kelvin, roughly minus 23 Celsius, a cold winter day. That's the highest anyone has reliably reached. Genuine superconductivity almost at the temperatures we live in.
Wait, that sounds like the dream. Why isn't that the headline instead of the fakes? What's the catch?
The pressure, and it's brutal. To make those hydrides superconduct, you crush them between two diamond tips to well over 1 million atmospheres, a couple of million for the best ones, comparable to the pressure deep inside the Earth, near the core. You could never run a wire, or a magnet, or a train on that. The sample is a microscopic speck in a diamond vise. And to be scrupulously fair, because this is genuinely different from the fraud, these results have been reproduced by independent groups, and in 2024, a panel of 15 leading physicists went on record that hydride superconductivity is real. So it's largely accepted science, with honest caveats. The Meissner effect, that field expulsion clincher, is only faintly seen in these tiny high-pressure samples, so much of the evidence rests on the resistance dropping and on trapped flux rather than the full signature. And one respected skeptic is still on record arguing the case isn't airtight. The picture, credible, reproduced, largely believed, at the pressure of the Earth's core. Not a fraud, and not, in any usable sense, a room temperature superconductor.
Let me hold all three heaps at once. The solid, superconductivity, superfluidity, DCS for the ordinary ones, the copper-oxide ceramics, the scanner and collider and floating train, all real, working. The open, after 40 years we honestly don't know how the copper-oxide ones work, a real unsolved problem, not a loose end. And the false or not yet, no verified room temperature superconductor at ordinary pressure, the two famous claims retracted with misconduct and debunked as impurities. But a real high-pressure frontier near room temperature, kept alive only by crushing pressure.
A flawless sorting, and keeping those three apart instead of mashing them into one blurry superconductor news is the whole skill I wanted you to walk out with. Here's the horizon I'll leave you on. There's a dream at the end of this road, a superconductor that works in your bare hand at room temperature and ordinary pressure. No coldant and no diamond vise. If we ever get it, it rewires civilization. Power grids that lose nothing, effortless magnets, machines we can't quite picture. We do not have it. We may never. Or someone may stumble on it next year. Nobody honestly knows. And between us and it stand two of the deepest open questions in physics. Why the copper-oxide superconductors even work, and whether that high temperature can be pushed all the way to warm without the pressure of the Earth's core. Both are open. Genuinely, right now, open.
And that's the part that gets me. Those aren't questions for some far-off genius in a story. They're questions with no answer yet, sitting right there.
Sitting right there, waiting. Everything tonight started in your homework. Resistance is electrons scattering off a warm lattice. Matter flips into new phases at sharp temperatures. One honest step past that, and you're at Cooper pairs and a single quantum state you can hold in your hand. One more step, and you're at a ceramic that floats a magnet in cheap nitrogen for reasons nobody fully understands. The frontier isn't a walled country reserved for other people. It's the next step past what you already know. And on this frontier, that step is genuinely unclaimed.
One honest step past the homework, and then the map just runs out. I came in thinking this was resistance going to zero and a phase transition, two things I'd already met, and it was exactly those two things, which opened onto something nobody has finished. Thank you, truly.
Anytime. Go find a video of superfluid helium climbing out of its cup. It's real, it's out there, and it looks like the laws of physics have a small leak in them. Then go do your next problem set, knowing that the strangest, most beautiful states of matter we've ever found are just a couple of honest steps past the page you're on.
I will. Until next time, keep asking where the textbook ends. That's where all the good stuff starts.